Okay. So there's the beginning of the sampling distribution, but we can't get the whole thing again because we can't, roll the dice, an infinite number of times. We can't. What should the center of this sampling distribution be starting to look like? 2.5. Yeah, should those two middle columns should be growing the fastest because of the way we've done this. Because we don't have a lot of data, they're not totally there the fastest. But we should be looking at 2.5 for our main. Okay, so for our center. Sorry. So my center should be at about 2.5 out of 5. So my center should be a half. What do you think the shape should look like? It should be getting, pretty much, in the tall centers, and we shouldn't be getting a lot of 5 out of 5 evens or 0 out of 5 evens. So there should be little tails at the end. So we could say symmetric or approximately normal. Yeah, we don't have enough data. And I bet we'd have a hard time figuring out what the spread of this one would look like. But let's just try to think of what the spread might be compared to the population. Well, it's going to be a little hard to say from what we have, but our spread is not going to be anything like the population. Because the population is a distribution of a categorical variable. So the proportions are kind of like doing the means, and we're going to handle them just like doing the means. Okay? So the center of our proportion, of our sampling distribution of our proportions, had better be the parameter of interest. The population is a categorical variable. Either you got even or odd. You got 2 bars, and they're both the same height. This distribution is not looking anything like that. So comparing their spreads doesn't actually make any sense. So, yes. So what should the proportion of evens be? Oh, I divided by the sample size. If I took all your number of evens and divided by how many times we were each throwing the dice, I'd want to get a proportion of evens. So since your sample size was 5, I divide by 5. Okay. Your standard deviation of this sampling distribution gets to be the proportion times its complement, or 1 minus the proportion, divided by your sample size, and then because it's a standard deviation, we take the square root of these. N is sample size. And these two come directly out of our study of the binomial. But we won't go back and look at the binomial. We'll just trust that this, looks like a binomial distribution. Okay. And this, let's see. Well, now we have to have some rules about this one because this one's a little trickier to use. This standard deviation calculation is only good if the population is a lot larger than the sample size, okay, so that in your book they call rule of thumb number 1. Nice, yeah. I don't know. I don't know why, but they will refer back to that as rule of thumb number 1, and so you'll say, okay, what the heck was that? That's the standard deviation. If the population is not a lot larger than the sample size, then we have a different calculation for standard deviation, and a lot bigger would be 10 times bigger. So our sample size of 5, 10 times 5 is 50. The whole population of the number of times you could roll that dice, it better be more than 50. Then we're okay. All right. The shape of our sampling distribution, which we decided was probably approximately normal, and I'll call this SD. It gets to be approximately normal. Sorry, sampling distribution. I should not have abbreviated it. My bad. Not yet, anyway. Approximately. Jeez. It says big pen, I think. There we go. Is approximately normal, and this is going to be rule number 2, and you'll love rule number 2 because we'll use it many times. If the sample size times the proportion is greater than or equal to 10, and the sample size times 1 minus the proportion is greater than or equal to 10. So this is rule number 2. Okay, so that we didn't meet rule number 2 in our little experiment, so our sampling distribution probably won't be approximately normal, because we did a sample size of 5 times a proportion of 1/2. That's 2.5, not greater than or equal to 10. Okay, so let's do one that is. Yeah, going back. It has to be both. And okay. All right. So this is rule number 2. Okay. There are many. There will be so many that you will go, I can't memorize all of these. But we're just starting off with 2 rules so far. You can do 2. Alright, so let's see how we can use these proportions. For example, let's suppose that doesn't look like suppose, does it? You're going to say that O-S-E. Suppose 35% of college applicants apply to more than one college. Sure. Okay, so we will test claims like this. All right. Greater than one college, using a little mathematical abbreviations here. Okay, you do a survey. You don't believe this. You do a survey. And you do a random survey, not just Aragon. You do a random survey of 1,500 students, seniors. And let's just say, what number did I put it? And you get a higher number. You get 38% in your survey apply to greater than one college. Okay? You do a survey. You go and ask a bunch of people, how many colleges do you apply to?